Okay, let's go ahead and get started today. I've got, looks like the majority of you are here, so I might be admitting a few more people as we go. One thing that's probably going to help today, once I get going with the whiteboard, is to make sure when you're in Zoom that you go up in the upper right corner and there's a gallery view or a speaker view. So when I'm speaking, that should take up the whole screen or nearly the whole screen for you. So then you can see the whiteboard better and go full screen. But also let me know if you can't see, if I can increase my font size as we get into some of the examples. But what I'd like to do every Wednesday is our synchronous class. And as we met last week, so this is our second synchronous class. Every time at the end, I will post this on Oaks. So if you could make part of it or miss some of it, you can always watch that recording. What I'd like to do every Wednesday is at the beginning of class, take any questions that you had from module 0, in this case, our orientation module. Pretty straightforward, but if we do have questions, we can take that in the beginning. And that might take up a certain amount of the class time, and then I may say, and that's as much as we have for that. I'll cut us off. I'll start a mini lecture. That'll go to the next section. And then if anybody wants to stick around and ask more questions, either from the previous module or the current lesson and future module. So we finished, so you did module 0, which is due tonight at 11:59 p.m. Last chance to enter anything else for your homework. And you could ask questions. That's why I thought Wednesday would be nice. But also on Wednesday mornings at 1 a.m., your next module opens up. So if you finish module 0, it's a good time now to start module 1, and you could bring questions for module 1 that you started watching videos or looking in your journal. Next bit of advice too, as you're going through each module, you'll see there's the course materials section, which says basically read a certain section in your journal. And then there's watch some videos. And it's nice to go back and forth between those. So watch a little bit of the video, do some pages in the journal, do some pages in the journal, watch a video, see if you can catch up with what's going on. And then you will see in the assignments section of Oaks, there will always be like a part 1 and a part 2. The part 1 is due on Sundays, the part 2 is due on Wednesdays. So like right now, if you go look at your module 1, just opened up this morning, things are due next Wednesday at 11:59, and there are Sunday due dates and Wednesday due dates, but always at 11:59 at night. And so you can go ahead and take a look at those, but if you look at the assignments, you'll see that they come directly from your journal. So it just makes sense to start working through your journal as you're going, and then some of those you have to take a picture of and submit. Okay, so I think what I'll do now is open up for questions. So you can either type in the chat, you can ask about logistics, you can ask about content for module 0, or if you want to unmute yourself and ask a question, now's the time for that.
I have a sort of technical question. I was trying to submit the 2 pictures from the journal.
Yes.
Sorry, I didn't have my video on. And it wouldn't let me, it literally wouldn't let me choose any files or anything from my computer. So I don't know if that's just my computer or if anybody else had that issue.
I don't know how to answer that. I'll probably tell you to go back to your syllabus and check for tech support. But if someone maybe had something similar, was it an Oaks thing, send it to the chat, reply to Alexia if you have advice on that.
Right, thank you.
Mm-hmm. Okay, a couple other questions in the chat I'm going to reply to. And so Annie asked a question. The group assignments, I think they specifically say in the instructions whether or not one of you needs to turn in or multiple. And I believe for the next question from Reagan, the team intro video, it just says one of you needs to go put that in the appropriate place in Oaks. Okay, and then Cheyenne asked a question. So there was some confusion. I do want to apologize for this. For some reason, another professor's Oaks stuff populated in my Oaks. IT couldn't really explain that. So that's what the study guide, all of a sudden there were some weird things appearing in your calendar. If you went to the course home, it's like things I hadn't mentioned or you hadn't seen on the syllabus. And one of those was the study guide. And it said it was due on Tuesdays. It also said we had a Zoom on Tuesdays, and there was a lot of confusion. I got several emails from folks. And that's why I sent the class an entire email. Again, Wednesdays and Sundays are our days. IT has taken that out. So you should just see my assignments now.
I got one question.
Okay.
In module one, I tried watching the videos. I guess they say they start on the 28th. So is that not related to what we should be doing this week? Or if I don't know if it's just my folks that's doing that.
Oh, I didn't. So let me check on that, Aaron. So you're telling me that your module one videos weren't appearing. They say they will be next week. So let me check on that due date then.
Days it starts October 28th.
It should be October 21st. So I'll go change all those then. And you can access those videos as soon as class is over. I'll fix that.
Okay.
Thank you, Aaron.
I have a question. On the syllabus, it says there's a study guide that's due, like a group study guide. Is that due next week?
No, I don't, that shouldn't be also be on the syllabus. Let me check a few things about that. It could be this other professor's Oaks stuff. So
Okay,
sorry, Lauren.
it's fine.
Okay, so again, let me just reiterate what you should be seeing on Oaks, and then I'll have to change some things, some settings. But you should see every week in your course materials for, say, Module 1 started this morning at 1 a.m. You should be able to access videos. Those videos will describe things in the journal. So again, they go hand in hand. If you're having trouble understanding what was on the next 10 pages in the journal, the videos are there to help you, and they'll complement each other. That's your course material, and then there's an assignment section in Oaks, and those assignment sections have things that are due on Sundays and things that are due on Wednesdays. But those are always things like choose two of these following 4 activities from pages such and such and such and such in your journals, put them in a Dropbox. Complete pages 57, 40, 44, and 72 in your journal and submit those in a Dropbox. And then there will be quizzes. So those kind of assignments is what you'll be seeing. And they all come from your journals, and then the quizzes are in Oaks. That's the sort of stuff you should be seeing. Okay.
Will you tell us like which book our homework can be found in? Because there are 2 different textbooks.
Good point. So Lauren's question is about the journals. There's 2 of them. We are working on journal 1, and we will be working on journal 1 for the next 4 weeks. The last 3 weeks of the class, we'll switch to journal 1.5. So everything from now on for the beginning of class is coming from journal 1. Just save that other one somewhere till later. Okay, so if there are no more questions, or as you think of them, put them in the chat. But I'm going to go ahead and start with a little bit of a lesson then. So we'll start working our way through the journal. You'll see some of this material, but also additional material in the videos that I made for this week. And as we work through the lecture today, it's a great time to be able to start filling in those pages in your journal. Like, I'll give you time to do some of those. And so we're already getting started on some of your homework. So let's just focus today while we're doing this together in class, and we'll get some of these homework assignments out of the way. Okay, so again, you want to go to the speaker view. So you can hopefully see me on the whiteboard. Should be bigger. And let's make sure that switches. All right, so hopefully again, you can see this. And if you're having trouble reading the size of the font, please put something in the chat and I'll try to write bigger. I think the darker pens work best, so we'll start there. Okay, so we are in Journal 1, Chapter 1. You've already read the preface for your Module 0 homework. And so the title of this chapter is the derivative. Some of you might have seen that in high school, but it's okay if you've never heard that word. We're going to go over it quite a bit in Chapter 1. And there's 2 types of lines we're going to talk about. So you can flip the page. We're going to be talking about secant lines now on page 24. So in Module 0 in the preview, you learned how to get slopes of lines, how to get equations from a line. Lines are what kind of functions? Linear functions. Because they're linear functions, there is no bend to them. They're straight lines. And so a function, y is a function of x, if you draw 2 points anywhere on this function and connect them with the line, that is a secant line. And so therefore you could easily get the slope of that line, right? Slopes, the slope of a line, we usually use the notation m. That's change in y over change in x, y2 minus y1 over x2 minus x1. I didn't give you an explicit formula for this function. If I had, you could go ahead and do this. You'd have the 2 points. This would be x1, y1. This would be x2, y2. And maybe let's say, just to make up some numbers, let's say this is actually the point minus 2, 4. And let's make up this one was positive 2, 5, something like that. Right, so you could plug those values in and get your slope. But one thing you can say from the way I've drawn the picture, is this line, is its slope, got to answer one of these 3, is the slope less than 0, equal to 0, or greater than 0? So just take a moment, think about that. Given this picture, my secant line is here. Is the secant line, is its slope negative, 0, or positive? Okay, hopefully y'all got that answer. Oh, hang on, I see something in the chat. Just to reply to Diamond quickly, the recorded lectures, like this class is recorded, and it will be posted in Oaks under, this one will be the module 1. There'll be another video to watch. It'll say recorded class from module 1. Will, we are on page 24 in journal 1, talking about secant lines. Okay, so again, y'all realize that this is a positive, so check here, positive slope line. So flip the page to page 25, you can get started with some of your homework. So let's just take a couple minutes and do a few of these. Work through these on page 25. I'll do number 3, and then you guys can start working. So work quietly, and I'm going to put number 3 on the board. Okay, I'm going to interrupt you while you're working on your problems, and we'll just take a look at number 3 together. So there's a graph of a function. I tried to sort of estimate it here, and there are 2 points. So if you connect those, it says the first instructions was draw the secant line. No problem, and we can all just connect the dots, right? Secant line, and then it says estimate the slope of that secant line. Okay, well this one's definitely a negative leaning line. Then we just have to figure out the slope, and yours has nice graph paper on there, so you can kind of count how many you're going rise over run. So it looks like about 3 in the x direction, about 3 in the y direction. So that'd be a 3 over 3, which is about minus 1. So we just needed to give it, it told us just estimate that slope there. You can check the other ones and notice for most of the pages in the book, there are answers at the bottom. So find me any errors that I've made. Also, in general, if you see any just typos or anything, I'd love to see that. I usually post a survey at the end of modules. So if you're finding any errors, collect them. They can be grammar errors, graphic design, math errors. I'm going to give you bonus for any ones you find. You'll help future students. So if you find them, collect them somewhere, maybe write them in the beginning of your journal, and then there'll be a place for you to submit those at the end of a module. Okay, so no problem with secant lines. And now we're gonna, the next several pages are road trip story, average speed, average rate of change. You're going to learn a lot about that in the video that you're going to watch this week. And so we're actually going to go up to page 31. And we're just going to talk about some vocabulary on this page. And so this page says that you can actually think of a nonlinear function, like the one drawn. If you zoomed in close enough and close enough and close enough, you'd actually see that the function looks like a line. If I just zoom in close enough, if you had, think about your TI calculator and you were just zooming in, zooming in, zooming in, rather than looking curvy, it starts getting linear. So, and this is true for any function. No matter how wavy and curvy I made it, if I just zoomed in, it's really curvy right here. But if I just zoomed in on that part, that little parabola, and I zoomed in again on that part, it's less curvy. And then I zoomed in again on that. Again, it's going to start looking more and more like a line as I zoom in. And this is the idea that a curve can actually be made up of many little line segments. So I could actually think about this as, maybe you can see the red, as just made up of a bunch of little line segments. So I can just string a bunch of, like, think about maybe little pieces of rice together, and I can string them all together. And even though each little piece of rice is a fixed line, together they can make something curvy. Now, why is that important? That's for the next idea. So we're going to have two types of lines we talk about. Secant lines, we already talked about, no problem. Give me 2 points on a line, connect them, and you have a secant line. They're pretty basic, but the new thing for us is tangent lines. And they're the ones we're going to use repeatedly this semester. We're going to talk over and over about tangent lines. And this idea of a nonlinear curve is made up of a bunch of little line segments, or linelets, they're called. Every little one of these is called a linelet. They're going to help us understand tangent lines. So flip the page on page 32. This is an activity you can choose to do for your homework. A lot of times for your homework, you have choices of activities. So maybe this is one you choose. You have to choose, maybe do 3 out of the following 5. So this might be one. You're going to write your name and you're going to write it in linelet font. That'll help you get an idea again about tangent lines. So now we're on page 33. And tangent lines have something to do with, again, if you've had some pre-calculus, you might have heard this keyword derivative. These two things are related, tangent lines and derivatives. We'll talk more about how they are related in a bit. But the tangent line really comes from this idea of thinking about a curve as made up of linelets. So let's flip the page to page 34. Talk about Barrow. He had this idea that no matter how curvy you were, you could think about drawing a tangent line that actually estimates the curviness, estimates that function at locally. Okay, so maybe I'll put a simpler function. Actually, you guys go to page 34. There's a function there. I'm going to try to draw my approximation of that function on the board here. All right, so we have y as a function of x. They didn't give us an explicit rule for that. They just showed us the relationship pictorially. That's fine. Then they had a couple points of interest. Maybe it looks like there's one about here, 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 here. All right, so this is about what you have on your book there on page 34. Oh, another comment I should say, as you're reading through your journals, you'll often see that there are things in gray, lighter font, gray font. And this usually, if you read the preface, those are your like action notice to like do something. There's your action alert, like, hey, do something with this like draw a graph, it'll tell you to do something. Here it's saying draw a tangent line at each point below. So I have to tell you how to do that. A tangent line does a good job approximating your function at the point of tangency. So let's take the first one. That's our first point of tangency we want to look at. And I want to approximate the function there with a line. I know the function's not a line there. It's actually curvy, right? It's got some bend to it, but I want to approximate it with a line. And so I can do that by thinking about the function as zooming in, zooming in, zooming in, and that linelet idea. And I'll just extend the linelet. So I zoom in, zoom in, zoom in, and it kind of looks like that. And I'll just extend that little approximation and create the tangent line. So that's one way to draw a tangent line, the zooming in idea. Just keep zooming in, zooming in, zooming in. So let's try that idea at another point. Maybe over here at the last point, let's try. If I zoom in, zoom in, zoom in, this function actually starts to look like a little linelet there. I'll take that little linelet and then I'll just extend it. So there's the tangent line. The tangent line, as opposed, the secant line goes through 2 points. The tangent line only touches 1 point locally. I'll explain a little more about what I mean by locally in a bit. Okay, so that's one way of thinking about drawing a tangent line. So that might be helpful to some of you, the zoom in linelet idea. The second thing, also on page 34, came from the guy who kind of came up with this idea of linelets, Barrow right there. The other way of thinking that he liked to think about tangent lines and functions, he liked to think about riding along on this function. And maybe for us, he didn't have these then, but for us, maybe think about this as like riding along on a roller coaster. Well, if you stop at any point of that roller coaster, the direction of motion is actually given by the tangent line. So let's take this fourth point over here. Let's imagine what would happen if we were riding along the roller coaster and the roller coaster derailed right here. Bad news if you're on the roller coaster, but for us, for math, we just want to know, where would the roller coaster go? What direction would it continue to sail? It would continue to sail in the direction of the tangent line. Now you would sail off that way. Or imagine at the amusement park in Virginia, there's a place called King's Dominion. You can ride something, they used to be, decades ago when I went there, you could ride the roller coaster in the forward direction. It was called the Rebel Yell, or you could ride it in the backwards direction. So now imagine riding in the backwards direction, and the tangent line does the exact same thing, which it has to, right? It has to make a line in both directions. So, sorry, go ahead.
I'm sorry. For the tangent line, so it never goes through, right? It just touches.
Great question. So I can't see because I'm in the spotlight view. Sorry, I apologize. I don't know the name of who just asked that, but great question, because the tangent line just locally touches at 1 point, but it could come over here and touch the function again. That's okay, right? It's also, it happens that this tangent line is the secant line between these 2 points, but what we're interested in is the fact that it just barely touches. In fact, tangent comes from Latin tangere, meaning touching or kissing, just like barely touches. So the function, the curve, and the tangent line just barely touch each other, right? So here's our curve, and then it just barely touches the tangent line locally at 1 point. Exactly 1 point there. And it only does, the reason I say locally, because of the great question we just had, it's only when you zoomed in close enough. It's okay when it extends if it touches, multiple times. Like this function might come on down over here and it might still intersect way over there. It could touch it multiple times, but when we zoom in, it only touches it just infinitesimally, barely touches it at that 1 point.
Thank you.
Yeah, great question. Please, and this is how we want it to be, like, if we were in class, it would be totally just like this, interactive. So interrupt me anytime or put something in the chat if I'm not seeing you. But it's great to just unmute and I'll be quiet for a moment. All right, so you can finish that and estimate the tangent lines at any of these other points. So let's put in a couple more here. There's a tangent line. This one looks almost horizontal, depending on where that circle point of tangency was. So a couple of points to be made about this. A tangent line can be drawn at any point on the function, and depending on the point, the tangent line will have a different steepness to it. The second thing to say about it is we can say each of these tangent lines, we could determine whether or not their slopes are positive, negative, or zero just by looking at the function line. This one's clearly a positive leaning line. This one's clearly a negative. This one's almost zero, it looks like. This one's positive. This one's negative, just barely negative. So maybe slightly, say slightly negative. Right, and that's useful information to us because it's going to tell us something about the rate of change for the function. And again, you're going to see some more videos and we'll get to more of that a little bit later. I'll come back to this rate of change idea. But for now, the key thing you want to make sure you can do is draw tangent lines. We're just asking you to sketch them. And there's two key ideas to help you do that. Zoom in, and do the linelet idea, extend the linelet. Second idea is use the Barrow's direction of motion idea, which is to just ride along the roller coaster and sail off at that point. So let's do a few. The next several pages are activities that you'll do to help you understand tangents. So I want us to do one together now, page 39. Okay, in this one, the instructions are that you are riding on the swings at a carnival ride. It's that ride that you think of a ring at the top and it has all these lines of little chairs at the end and it's swinging around and goes in circles and then lifts up higher and higher, right? Imagine at some point as you're swinging around that, you're wearing flip-flops and one of them flies off. What direction would you go to find your lost flip-flop? And so that is on page 39, the first one. Says you're traveling like in this direction, going this way around on the swings ride. Your flip-flop flies off right there. Where should you go look for it? So take a moment, do it in your notebook or right here in your journal or at the very top left one. So take a moment and put the direction of motion. Where would you go look for it? If your flip-flop flew up right here, where should you go look for it? If you did that one, take a moment and go ahead and start completing the ones below it. Similar idea, but sometimes the swings are traveling in the other direction. Sometimes the point of where the flip-flop flies off is different.
I'm sorry, what page is that on?
Page 39. So I'm always going to try to write them at the top here, the pages as we go. Okay, so for this one, this is on page 39, the one at the top left. If you're traveling this way on the swings and your flip-flop flies off right here, another way of saying that is just find the tangent line, the direction of motion. Where would you sail off? Flip-flop would have flown off in that direction. It's really asking you to get a tangent at that point. So you can complete the ones below it using that same idea. The second one, just below it, still riding the swings, but now we're going in the other direction this way. Flip-flop flies off at almost the same place. So now I'm riding around and I'm going to draw a tangent. It's the direction of motion. If you were to derail right there, which your flip-flop does, flies off, this is the direction you'd start walking to look for it once you get off the ride. Okay, now on the other side, the right-hand side of that page, it sort of flips the problem around. So now we're over on this side. So if this was like 3, 4, I should put numbers, I see that now. 5, 6, let's look at the one up at the top. We're still going this direction. Your flip-flop is over here. And now it's saying, where must it have come off? Some park employee went and found it over there. Where must you have been for it to have sailed off? This is also another question about tangency. It's just saying, it clearly you couldn't have left here because the tangent would have been that way, right? It couldn't have left here because the tangent would have been in that direction. It has to be somewhere around about here because that's the direction that would intersect with the point outside the circle. So all of these are tangent lines. They exist at any point on this circle. The one we're interested in is the one that intersects the point outside the circle. These ideas are really powerful because then you can solve some really neat problems, you'll see with your challenge problems. Another good thing to do when you start every chapter of a module is to go read the challenge problems at the end, because they help. You have to submit them with your team, but they also help as you're going through the journal to constantly have that in the back of your mind. Like, how can I use what I just learned about secant lines? Does that help me with the tangent, with the challenge problem? Maybe not. Okay, how can I use what I just learned about tangent lines? Could that help me with the challenge problem? Maybe I got an idea, right? So it'll help motivate you as you go through the chapter. And that's the point, right? We're trying to get to those challenge problems, which actually serve as our exams. And you get to see them in advance, work them at home, work them with your team, and ask me questions as we go. Okay, so that's an activity. You finish that one, and this could be one that you submit for your assignment. So we're going to get part of our homework done as we go. Okay, flip the page, page 40. Okay, now here's the idea of what happens if we have like a function that's not, and there's a couple drawn here. This is a good one to also do as an activity, but I'll just draw one, make up my own. Y is a function of x. And one thing you can notice is that it's nice and smooth, and then there's this jagged point here. And what is different about this point, this one's actually a special point, it's going to be called a non-differentiable point. Lots of syllables, but really non-differentiable points just means that you don't have a derivative. Again, I haven't really told you what that meant, but it also means for us, those are places where if I'm riding the roller coaster in the forward direction, I would sail off like this. If I'm riding in the backward direction, I would sail off like that. These two tangent lines don't match. When that happens, one time that can happen, is at a non-differentiable point. When the two tangent lines riding the function forward or backward don't match, you have this special point, non-differentiable points. Everywhere else, any other point that you were to pick, there's infinitely many points on this function. Any other one you were to pick, riding in the forward direction is the same as riding in the backward direction. They create the same tangent line. They create the same tangent line. Riding in the forward direction, riding in the backward direction. They make those two tangent lines match. And again, they have to. That's because the function is something called smooth and continuous. So a couple more vocabulary words for us. Your function smooth kind of makes sense just the way you think about it. There are no sharp, jagged points. It's continuous means there's no discontinuities. Another way of defining it in terms of its absence. There's no discontinuities, which are places where you have like an asymptote, where you have to jump over. Something you might have seen also from high school classes, like a discontinuity. Something like that. And those are not continuous because as you trace the function with your pencil, you have to pick it up off the paper to get to trace it. Same thing here. If I'm tracing the function, I'd actually have to pick my pencil up off the paper and come over here. On the other hand, this function is continuous everywhere, but it's non-smooth at this point, this non-differentiable point here. Lucky for you, in business calculus, almost all of the functions that you will face when we'll be talking about minimizing costs and maximizing profit are smooth and continuous and differentiable everywhere. So those are like the ones I had kept drawing, right? These kinds of nice, well-behaved, nice curvy things, no jagged points, no holes, jumps, or breaks. But it's nice to know that these things exist and what that actually means. So you can finish on page 40. This is yet another activity you can do at home to finish. You should have the idea now of what it means to be non-differentiable, and you can find the error associated with that page. Okay, page 41. Okay, we know how to estimate, visually estimate drawing a tangent line and estimating its slope. Is it positive, negative, zero? Is it steep positive? Is it kind of shallow? but our goal is to get this slope exactly. It's going to take us some time to build that up, but let's say this is a function you're going to see in the videos this week quite often. It's called the road trip function. And it does have an explicit formula, 5x squared plus 50x. It's a nice polynomial quadratic function, well-behaved, smooth, and we're just going to define it from 0. I think in this case we go from 0 to 4. And the reason it's called the road trip function, you'll see from the videos that you watch, which I will make sure they're open correctly from Aaron's question earlier. Those videos describe us. We all get in a bus, we leave Charleston, and we go to Raleigh, and we start off slowly, and then we start accelerating. And this road trip, when we take secant lines that get their slope, they mean something. They mean a type of rate of change. So again, you're going to see this in the videos, and you're going to learn about average rates of change. And that's as opposed to tangent lines, which are instant. I said rates of change before. These are instantaneous rates of change. Again, you're going to hear a lot more about that, so more will be revealed in the videos. I'm just going to give you a preview. And the preview is that if I took any 2 points, connect them, that's a secant line, no problem. And maybe I did these 2 points and connect them, that's a secant line. These 2 points and connect them, that's a secant line. So we have a bunch of secant lines. But we're interested in, instead, at this red point, we want to get the tangent line, which we know how to draw. Ride the roller coaster, that's a tangent line. We zoom in, think about the linelet, extend the line onto a line, we have a tangent line. So 2 ways of doing that. We know how to estimate that. We also know from this picture, it clearly looks like the slope of the tangent line is positive, but we want to know exactly what is that. It's a positive number, but what is that positive number? And we're going to do that by learning how to take a derivative in chapter 2 of this function. So again, just a preview for some folks who may have already had this. The derivative of this, just some notation, is itself going to be a function that is called f prime. This derivative function gives us the instantaneous rate of change, which is exactly the slope of this red line at this point of tangency.
Sorry,
Go ahead.
Can I ask a quick question?
Mhm.
So for the T line, would it be, is that like where you're starting for making all the other secant lines?
Great question. Yes, that is also often called the point of tangency. And I'm going to go some distance. Again, I'm kind of previewing some things you're going to see in your videos. I don't want to be redundant, but I'll just give you a little bit of the idea here. This point of tangency, I'm going to go a little bit away from that and draw a secant line. A little bit away from that, draw a secant line. A little bit away from that, and draw a secant line. And I could do that, or really what I usually do is I go the other direction. I go some distance from the point of tangency, make another point on the function, that's a secant line. Actually divide that in half, get to another secant line, divide that in half, get to another secant line, and so on and so on. These secant lines eventually have to converge to the red line, right? If I keep shrinking the space between the 2 secant points, those 2 secant points are just so close to each other that they're almost touching, they're almost one point, the point of tangency, and therefore the slopes of these secant lines converge to the slope of the tangent line. And so that's a great question. In fact, it makes me think we should jump ahead to something else, to this gallery pages. Okay, so this is on pages 54 and 55. There's these gallery pages. So go ahead and flip ahead. I'll write it up here. Okay, so what happens, I'm not gonna draw all those pictures. I think that's gonna be too hard, too time consuming for me, but what we're doing here in the upper left is we have a function, a nonlinear function, right? From module 0, we know that's nonlinear. We're gonna draw a secant line, and we're gonna do it between a point here, and we're gonna go some distance away and also be on the function. So we'll be at another point on the function, connect those two dots which live on the function with a line, we create a secant line. And we're gonna do that, but we're gonna shrink the distance between the two secant points as we go down. Keep shrinking the distance, and then we'll go over to the top up here. Keep shrinking, and that's the little bar at the bottom. H is the distance between the two secant points keeps shrinking. And the tangent line is the dashed line. That's the one you know how to estimate already visually, right? And that stays the same in all the pictures. What is changing is the secant line. And as H, the distance between the two secant points shrinks, the black line gets closer and closer to the dashed tangent line. That has to happen, right? That has to happen. Another way of thinking about it, I think I asked you to do this earlier also. This is one of your homework assignments on page 46. That's the same fingerprint function. There is a point of tangency. There is a dashed tangent line. And then the assignment asks you some things about this line. And then it says use the bottom corners in gray as a flip book. And so you can do this right now. Notice on the next several right-hand pages, there is that little fingerprint function. So if you do it as a flip book and watch that fingerprint function, the secant lines converge to the tangent line as you flip through there. So that's another way of animating what is on pages 54 and 55. This idea that the secant lines have to converge to the tangent line. Okay. Next couple of things I want to talk about. We'll come back to derivatives, and you're going to see those as well in your videos. I want to talk about now on page 57, 2 more vocabulary words. Increasing and decreasing. This is really simple. These terms are just like they would be in English. There's nothing special about using them mathematically. It just says, if I have a function, something like this, I am increasing whenever I would be imagining now, this is like I'm pedaling my bicycle. Pretty flat here, now I'm going steep downhill, pedaling, working hard, going uphill, downhill, uphill. Increasing is when you would be pedaling your bicycle and going uphill. It's a lot of work. Downhill, coasting, that's decreasing. So you can think about this as like pedaling uphill on the function. And this one would be pedaling downhill on the function. But so take a moment now, this picture I've drawn, I actually just copied from page 59. On the bottom, turn to page 59. At the bottom, there is a little drawing. I'm actually kind of proud of that guy on the bicycle. That took me a bit because I'm not an artist. But go to that function here. And I want you to shade, like darken in on that graph where you think it's increasing. So just imagine you're actually riding your bike on that. Where would you be pedaling uphill? So shade that. Take a moment right now and do that. And that's on page 59 now. Okay, hopefully you guys all started shading right about here. I'm pedaling uphill until about right there. Then it levels off for a moment, and then I start going downhill. Right at the bottom of this hill, I have to start pedaling again. Well, you could be coasting, but. Okay, so those are the sections where this function is increasing. But now I want you on those squiggly sections that you drew. Stop and draw on these sections. Maybe let's put in, I don't know, let's say 10 points of tangency. So stop and draw 10 points anywhere on these squiggly sections. So I'm going to just put some of mine in here. Okay, so I drew 10 points in red on those squiggly sections. You've got 10 points, probably pretty similar places, I would imagine. Now draw your tangent lines at each one of those points. So you should be giving me 10 tangent lines. You should be good at this already. 2 ways of thinking about it. When you draw a tangent line, you're either riding the roller coaster and imagining you're sailing off, or you're zooming in, zooming in, zooming in, taking the linelet and extending it. So however you like to think about it, draw me 10 tangent lines. The tangent lines will be different because we're at 10 different points in the function. So I'm going to draw mine, you draw yours. We'll reconvene in a minute. Okay, what can you say now? You've got your 10 tangent lines, I've got mine. Any questions on mine? Okay, now next question. What can you say, either look at mine or look at yours, what can you say about the slopes of these tangent lines? I drew 10 tangent lines so I can think about 10 slopes. Are those slopes positive all the time? 0? Negative? Do they switch sometimes? Some of them are positive, some of them are negative. Look at yours, look at mine. What can you say about the slopes of these 10 tangent lines?
They're all positive.
Awesome. So because they're all positive, that will always happen whenever your function is increasing. The slopes of the tangent lines are greater than 0. They have to be positive on any section for which your graph is increasing. Right, so we're actually pretty far along in calculus already with that one idea. That helps us quite a bit because we're going to use that repeatedly in chapter 2 a little bit, more in chapter 3, and in chapter 4. The idea that when your function is increasing, you're pedaling uphill, the slopes of your tangent lines are greater than 0, which is another way of saying that your derivatives, which just to introduce you to some notation, you're going to see f prime of x is also greater than 0. So this word derivative, we're also going to denote that f prime of x. So we have a function f of x. We can derive another function associated with that called the derivative function. And that must be positive whenever we're increasing. Okay, so now do the vice versa. Now what are the sections of the graph where you're actually going downhill? Mine looks kind of level here, so I'm going to make that actually level. This little section right here is neither increasing nor decreasing. It's actually just flat. This one actually has a slope of 0. Those will be important for other reasons, but every other unmarked section of the graph, here, 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 they're all pedaling downhill or coasting downhill. Those are all decreasing sections. What can you say always about any point where you would draw a tangent line? Their derivatives have to be negative. So whenever your function is decreasing, the slopes of the tangent lines have to be less than 0, which is the same thing as saying the derivative is less than 0. So these are the blue sections here on the graph. Okay, so questions for me? Okay, good. All right, so now I want you to go to page 60. We'll get a little bit started on another homework that you have this week. Okay, this is Page 60, also notice sometimes I have little time, what am I think are time estimates for how long it might take you to do this activity at home, if it's one you choose to do for homework. And then in the light gray font, that's kind of like, hey, you have to do something. You have to create your own texting function. So I want you on this graph here to draw from, these are hours along the x-axis from 0 to midnight, or let's see. Yeah, 1 a.m. until 11 p.m. And you want to think about how many texts you send or receive at different times of the day. And so I want you to draw a smooth continuous function. So hopefully during class, you've got your phone off, you're not doing any now, but make a smooth function anyway. It could come down and be 0, right? Where's 4 p.m., right? You should have had a big dive, 0. But it is smooth and continuous, so we just kind of bend that a little bit more. So you draw that at your desk right now, which you think represents a function that represents your texting behavior over the course of an average day. All right, now I'll do the one below it. It says, there's another little graph. It says graph the texting behavior of a parent or grandparent. Probably that's quite a bit different than yours, to draw another graph. Okay, once you've done that, one last one, if you want to pick a best friend, put them on the third graph, or just do something that you think might be quite different than the other two. Okay, I actually have I have not upgraded to a smartphone. I actually have a dumb phone, a flip phone, purposely. But I don't send or receive texts because they're basically like cave woman, like grunts back to something. So I really try not to get into that too much. But I did get a couple today from my the test of the Cougar alert system. So mine would look something like this if I was going to try to draw a smooth one. Like maybe at like 6 a.m. they had one for me. And then again, I'll try to smooth that out so it's not jagged points. But and then I think they sent us another one at like 2 today. So, but otherwise, that's my graph most days. Yours will be different, much more interesting, and again, a number of texts along the axis here. But let's make one that's not mine. Let's make one that's a little bit more interesting and put in the hours of the day. So I'm just going to make up something, maybe like, let's say this is 6 a.m., 12 noon, 6 p.m., and then 12 midnight. And this is, again, time in hours. Along the x-axis, y is number of texts. And let's just make up something here. Let's say nothing, and then there's like a spike I'm sending or receiving, maybe a lot right before dinner, and maybe not so much. So let's say that's kind of is it continuous? Yes, I can trace it without picking my pencil up off the paper. It is, there's no asymptotes, holes, discontinuities, jumps, or breaks. Is it smooth? Yes, I kind of curved things out. I didn't have any jagged points, holes, jumps, breaks, or discontinuities. So we followed the instructions. We graphed a smooth continuous curve that approximates, I kind of lied, this is not my texting behavior, but could be someone's. And then we want to answer some of these questions based off this texting behavior. And this will really help us, I think, personalizing the experience to something that you probably deal with every day will help you remember the meaning of these terms. And so the first question is on the right-hand side of that page, what are the units for the function? And then what are the units for the derivative? So I'm gonna have to tell you a little more about the derivative, but we can answer that first question. What are the units for y as a function of x? So again, this represents this curve represents y as a function of x. X is time in hours. You give me time in hours, this function will spit out, it's showing it pictorially, but it could spit out if it had an algebraic expression, it would spit out the number of texts that happen then. Right, so if I asked you, let's maybe put some units on this, let's say these are like, I don't know what's normal, do you guys do like, maybe let's say this whole thing is like 20, right? So this would be 10, 5, 15, is that reasonable behavior? I don't know, let's just go with it. So nothing happened, and suppose they wanted to know how many texts are being sent exactly at 12 noon. How would you answer that? You'd look at the graph, and you go to the point at 12 noon, that's your x value, and you go up to the function, and its height looks like a little more than 10, maybe about 11 texts. So this would also be the point, if this is time in hours past midnight, then we would say this is x equals 12 right here. So this is 6, 12, 18, 24, right? So at 12 noon, we had 11 texts. And then at 6 p.m., that looks like right about here on the graph, which is a height of about 16. So this would be 18. When x is 18, which really corresponds to 6 p.m., there were about 16 texts being sent. So it's the number of texts. So again, this function, you input x value, which represents the time in hours past midnight, it'll output the number of texts. So think about, do this motion when you think about f values. F values are heights on a graph, right? So you're always going up and down. That's as opposed to derivatives, which are actually slopes of tangent lines. So let's say at x equals 12, we were interested at 12 noon. That is, in notation, f prime of 12. That means the exact same thing. This says, find the slope of the tangent line when x is 12. This is just a compact mathematical way of writing all those words out. But mathematicians are lazy, so they like to make notation for things that are used often. So rather than saying, find me the slope of the tangent line at x equals 12, right? Find the slope of the tangent line at x equals 12. That is exactly the same, equivalent to saying find f prime of 12. Okay, so we can do that. We can estimate it now visually by drawing a slope of a tangent line. We've gotten good at doing those. So I would stop right here at 12 noon, draw my tangent line, riding the roller coaster forwards, riding the roller coaster backwards. I sail off like this. Here's my tangent line. It's positive, I can say that. We know then that the function is increasing there, which means as I go from left to right, I'm pedaling uphill. And so that's the next question. Question 2 here. So now we can answer this. I'm going to get this page done. So you get part of your homework done. What are the units for f prime? What are the units on the derivative? Well, the derivative is the slope of a tangent line. So what kind of units are actually associated with that slope? Remember how you get slope. Slope is change in y over change in x. So if we were given an explicit function, we could give you changes in y's and changes in x. X's as those secant points get closer to the tangent point. But think about what are the units on y? Number of texts. So this will be number of texts divided by what are the units on x? Hours. So notice when you read it that way, number of texts per hour, that's a rate of change. An instantaneous rate of change. At exactly 12 noon, the instantaneous rate of change is whatever this slope is. Let's just make up a number for now. Let's just say it was 4. We'll learn how to do this later. Suppose it was 4, then that would mean that the number of texts per hour that are your rate of texting at 12 noon is about 4 texts per hour then. Let's see, what else can we say from this graph? Oh, it asks the next question. And you can answer this for your specific graph. Is the derivative positive, negative, or 0 at these different time units? So it asks at 8 a.m. So that is about here. on my graph, and you would do the same on your graph at 8 a.m., the derivative is positive. So I would answer that because the slope is positive leaning. We also know the function is increasing. That's another thing it tells us. We answered the one at 12 noon. This one was positive. And then at 6 p.m., here's our tangent line at 6 p.m. That one has a negative slope, and we also know that it's decreasing. Maybe that makes sense. I have less text. The rate of texting per hour is decreasing for dinner, homework, whatever, bed, pre-bed, bed. So you can now complete that for the 3 graphs that you've drawn. You can answer those same 3 questions about the rate of changes and know that the units, this would work for any problem. If we're talking about, some of you might be like biomajors or chemistry or something. Let's say we're talking about, often you see something like this. Y is number of bacteria in a petri dish. This is time in hours or days or something. Let's say days to keep it different. And you're monitoring this. You're working in the lab. You have to go in and keep doing this every day or multiple times a day. And maybe it does something like that. Then the rate, then the units on, in this example, the units on the F, the function Y is a function of X. The units for the function would be number of bacteria. But the units for a derivative, which is a slope of a tangent line, would have units of, it's a change, a slope is a change in Y over change in X. So it would be, the units for F prime would be number of bacteria per day, which again creates a rate. And this rate is an instantaneous rate of change, exactly at whatever time they were interested in, whatever day. Day 7, you tell them exactly what the instantaneous rate of change is. Okay, I'm going to pause there and see if you got more questions for me.
So for those 3 questions on page 60, we are just answering if it's positive, negative, or 0, correct? We don't actually have to find like the exact number.
Great question. And could you? So you just have to answer positive, negative, or 0 by looking at the slope of those lines, right?
Okay.
We couldn't answer an exact rate of change because we haven't learned how to do it. They'd have to give you, I wish I could see your all's name. I hate not being able to say names. They'd have to give you, right, something like this. I'm just making something up here, like. Right, they'd have to give you an explicit function. And then in chapter 2, we will learn how to get that slope exactly. We won't be able to just say, oh, it's positive, or it's really steep positive, or it's barely positive, it's almost 0, it's negative, it's really steep negative. We won't be able to do, we can only say that now in chapter 1. In chapter 2, we'll be able to say, oh yeah, it's really steep negative. In fact, it's negative 11. It's negative 11.754, right? We'll be able to give very precise values once we get explicit functions, first of all, and learn some rules about how to take derivatives. In chapter 1, that's a great question because I should have said this already. Chapter 1 is about the ideas of calculating what we're going to calculate in chapter 2. We want to build up this framework for why we're doing this, what it means visually, what it means with our vocabulary, why we would care to do it. So we're going to have a couple applications this chapter, and then we'll get down to specifics in chapter 2. Okay, if you got more questions, put them in the chat for me. We'll continue on then. So that was page 60 was an activity. Another activity is on page 61. Again, activity pages have that graph paper background. So this is another one you can do, very similar. But you're again getting the sense for your vocabulary. Once you personalize and visualize things, it'll make sure that studying and these terms are going to be very easy. All these terms over here, increasing, decreasing, rates change, it's less memorizing formulas because you've done these activities. Okay, next thing, let's go to page, I encourage you to use tech tools this semester. So if you got a calculator you're familiar with, you can use it, but I'm going to show you some free ones online. And in fact, I'll do some of that right now. So let's go to page 62. And this is about, I'm calling them tech tools, technology aids. We're always going to be finding free ones online. And a couple of the most popular we're going to use are Wolfram Alpha and Desmos. Okay, so I'm going to share the screen and just go through a couple of these. Just show you that you can graph. Hang on, before I do that, I see something in the chat. So let me answer that. Addie also asked the same question as Aaron. I need to go into Oaks and change the opening dates for module 1, chapter 1. It should have opened this morning at 1 a.m. So as soon as this class is over, I'm going to open those videos. You can start watching them, completing pages in the journal, and everything will be set. It should have been the 21st, which is today. So I need to go change that. It will be done as soon as I finish class. Okay, but we're now on page 62 in the journal, and I want to introduce you to a couple tech tools. So I'm going to share the screen. And go to Google, just type in Wolfram Alpha. And this is a computational intelligence. It's supposed to be like a search engine, but they say it's less about search engine, it's a knowledge engine is what their idea is. And this is really useful. It has lots of math, science, and technology. You can type your question right here in natural language processing. So we want to graph, often we want to graph functions in this class. So like the first one on page 62 is graph y equals 4 minus x squared. Some of you might recognize this from parabola facing down, shifted up 4 units from a pre-calculus class. That's great if you recognize it. If you don't, we're going to have tech tools that we can use. So it's just saying, I want to plot y is this. You can check that you've input things right. They have this extended keyboard if you're looking for like square roots or something, but often you can just go ahead and type the square root. So like if I wanted to look at what the modified function y equals square root of, I could just do that, sqrt. So there's a lot of shortcut commands for these things. So you can practice doing those. Maybe I'll do number 2. Graph y equals x squared e to the x, because often we want to take a look of e up to the x, and once you type it in, make sure that it looks the way it should, like these are exponents, right? Check here, and then there's our plot. But the unfortunate thing here on Wolfram is unless you buy Wolfram, what's it called, Wolfram Pro, you can't like modify this graph or zoom in, which is why I like to also use Desmos. So let's go to Desmos. Desmos calculator. This is free as well. Probably some of you seen this from high school. So those same functions, y equals 4 minus x. Do the up caret, gets you to the square. They also have hints on how to use this. Ask your classmates, bring me questions if you just can't figure out how to do something in a tech tool. It's usually very easy for me to show you. Check that it works. It's often nice to put in functions that you know just to make sure you're using the tool correctly. Let's see what else on this tool. This tool over on this side here has some gear settings like projector mode. You can change the domain right here. This is like in your TI calculator, the window button. So you can change zoom in or zoom it out here. And this is also, hit that again, it goes away, zooming in and zooming out. Okay, now there's also another really nice feature. So skip ahead to page 66. And it's another tech tool page, just giving you hints. Desmos has something where you can trace the tangent line over time, which might help you with a challenge problem in this chapter and the next chapter. So I'm just giving you a strong hint here how to use this tool. And so on page 66, number 1 says, let's look at the function y equals x cubed. So I'm going to change this to y equals x cubed. That's the cubic function. Hopefully, again, you recognize that. I needed to actually, let me get out of here and show you. I needed to Google, so let me go back. Yeah, I want to leave that site, go back, let's go to Google. And when I just type in my URL bar, that's actually searching in Google. So I want to Google on the phrase at the top there, Desmos tangent line calculator. Let's see, I think this one does it. Okay, so this has got a preset function, sin x 0.3x. We don't do things with trig functions this semester. And again, we were interested more in x cubed for number one. There is our function in blue. And now this slider bar is actually going to show you in red the tangent line as you're moving along this function. So this little dot here, this little purple one, is moving along the cubic, and it's showing what the tangent line looks like. And that's pretty cool because you're going to see, again, if you take a look at, I think it's challenge number 2 at the end of chapter 1. This is a really useful hint for that. And I think this red dot, let's see, I think that's actually showing you the slope of the line. So the slope is positive here on this red line right now, but when I get closer and closer to 0, the slope's actually 0. And then the slope is positive again, steep positive, it's getting steeper, steeper, steeper. And we can see that that red dot is actually giving the exact value of m for that tangent line. Again, we don't know how to compute that just yet. We will in chapter 2. Okay. All right, a few more things for this chapter, and then I'll let you guys get to the videos, watching it on your own. Another key term is back up one page to page 65. And something called critical points. Okay, just like most books, gray boxes are usually important ideas. Call outs on the side are, again, important ideas. We've already seen the word non-differentiable. That's a place where you don't have a derivative. You don't have an f prime, because riding the roller coaster in one direction or the other, you get 2 different directions of motion. So we already talked about that term. But let's talk about this one, critical point. A critical point, the definition, it's a place, an x value, where your derivative is 0, or it doesn't exist. Now, again, I have to put the or doesn't exist for the people that are math majors, but you guys, somebody wants to get in class, Olivia. You guys are not, so we're business calculus, so we're really focusing on that first part. For us, a critical point is a place where the derivative is 0. So let's just visually see if we can find some of those. I'm just going to make up a function here. Maybe I'll do something like that. Y is a function of x. Is this function continuous? Yes, everywhere I go, I never have to take my, when I trace it, I don't take my pencil off the paper. Is it smooth? Everywhere it's smooth except right here. That's the only non-smooth point because it's jagged, it's not smooth, right? But also I would sail off in 2 different directions. If I'm riding in the forward direction, riding in the backward direction, right? They don't match, those 2 tangents don't match. Therefore, this is actually a non-differentiable point. So this non-differentiable point is a place where the derivative doesn't exist, because again, it doesn't have one unique tangent line. That's that special case that math majors focus on. So we're always going to have nice smooth functions. So let me just smooth that one out right there. Okay, now we'll look at places where the derivative is 0. So the derivative is a slope of a tangent line. So we're just trying to find places where our tangent line has a slope of 0, which is another way of saying places where you have a horizontal tangent line. So draw this in your notebook, in your journal, draw this function, take a moment and identify any places that you think are critical points, which means the derivative is 0, which means it's a horizontal tangent line. So identify those for this graph. You should have 5. Okay, I see a question in the chat I want to answer before we come back to our 5 critical points for this function. So Trinity asked a question for the tech tool pages. What do we have to submit in OAKS for our homework for those? And what you should see, should check, because again, it's been so crazy with OAKS this semester. For the tech tool pages, I'm just asking you to go through them. You don't have to submit anything. Usually that's like the top instruction, the first line, and in the text when you go and look at that assignment. So it'll say do tech tools, but there's nothing to submit. Other times it'll say do activities and there is something to submit. You take a picture of your work, do calculation pages, take a picture of your work. Okay, great question. Thank you, Trinity. Now on to our critical points. Critical points by definition are a place, points where x values, where f prime of x equals 0. Well, when does that happen? Those are places where you have a horizontal tangent line. Okay, there's one right here, one right here, one right here. Now, what do you notice? Why do you think critical points get the adjective critical? What makes them so critical? Well, for us, one of the main things we're trying to do in this class is, because it's business calculus, minimize cost, maximize profit. This function might represent a profit function, and we want to know where are the places where you have maximum profit. And sometimes the function is not something that we can even graph because we're actually in higher dimensional space. We'll get to that way later in the semester. So you don't always have a graph to go on. In this case, we do, and we can visually check it. But critical points in this case, every single one of them is either a max or a min, right? This is the maximum of all of its neighbors. It's the tallest nearby. There's like peaks or valleys, right? Peaks, valleys, peaks. Those are important points. They're critical because they could be places where you are the maximum profit, the minimum cost. This is minimum for its neighbors nearby, but this is the global minimum. This is what we're eventually in chapter 4 going to call a local min. This is what's called a global min, bigger than everybody, smaller than everybody on the graph. Okay, so again, you should be able to estimate those visually from a picture. You could use a tech tool to estimate them. You're just waiting for that red line in the Desmos tech tool we just used. You're waiting for that red line to just level out, and it would have a slope of exactly 0 there. So any places as you're riding along that curve where you have a horizontal tangent line. Another way of thinking about critical points in this case is if I'm riding my bike, it's the place where I stall, like I'm uphill, stall for just a moment before I go downhill again. Or vice versa, downhill, stall before I gotta get going uphill. Okay, let me do one more though, because it looks like from this example, every critical point is also an extrema point, which means like taller or smaller than its neighbors. It's an extreme, right? Most optimized point. But here's a classic function. We'll just put it below it. This is y equals x cubed. This is actually a critical point right here at 0. In fact, we just did this, right? We just did this on the tech tool with Desmos. It leveled out exactly right here. This is a tangent line. The tangent line is the x-axis right there. So here's an example of a critical point at x equals 0, has a horizontal tangent line. The slope of that tangent line is 0, and yet it's neither a max nor a min. So again, I'm kind of previewing things from chapter 2 and 3 that we'll get to in a moment. Okay, so lots of terms, and we want to make sure we can visually identify these things in chapter 1. Okay, a couple more pages I want to go over. Well, I got you. I won't keep you too much longer. I'm going to try to go to like an hour and a half, hour and 40 minutes, and then save time for any other questions you have, things that you might be, probably more like next week where you'll have, hey, we got homework due, and I need you to go back over some things from module 1. Okay, so this is now page 67. Okay, the concept on page 67 is that if you're given an explicit function, this is going to be from the road trip story, but maybe this is number of texts that you send. This was the example where X was the time of the day in hours past midnight, and Y, because remember Y is always a function of X, Y was the number of texts. Then if I took the derivative, this is also a function. You input an X and it'll spit out now a steepness of the function. So I just want to make sure we understand the difference between f and f prime. The function, you input an x, so maybe let's do like a little function box. X comes in, it spits out a y, it does whatever the rule tells it. In this case, if you sent in x equals 1, it would take 1 and square it, multiply by 5, that's 5, 50 times 1, so 5 plus 50 is 55, it'll spit out. If x was 1 came in, it would spit out 55. That is a height on the graph. That is when x is 1, y is all the way up there at 55, right? And that is the distance right there. That is the height value that it's giving you. That's different than this derivative function. Again, don't worry about how we got to this derivative function. We'll learn how to do that in chapter 2. Just assume this is correct. This is the slope of the tangent line for any x. You put in an x. So this one's box looks like this. Input is x. It outputs f prime of x. So if you input x equals 1, it's going to spit out f prime of 1. And you follow the rule. In this case, the rule turned out to be linear. 10x plus 5 is a linear function. 10 times 1, 10 plus 50, 60. If we're doing the number of text scenario, this is now number of texts per hour. Those are the units. Number of texts per hour. Whereas this is number of texts. Right, so I'm getting x time in hours. Y is number of texts. Okay, now again, this gives you a height, whereas the derivative, I don't know what the function looks like, but when x is 1, I'm actually at this point on the surface, I have a really steep tangent line with a slope of 60. Right. So just visually one more time, y is a function of x. The original function tells you heights on a graph. You're going to do things like this with your hand. Derivative at that point tells you how steep you are, right? It's like this kind of motion. So two different, if you get these, this is going to set the path for you going forward this semester. This is a major, major point. The original function takes an x value and spits out a height, how tall you are on that graph. The derivative takes as input an x and spits out how steep you are at that point. And remember, the steepness approximates the function, right? So I know that the function is really steep. This is like crazy pedaling uphill on the function. Again, I don't know what the function looks like. I didn't try to graph it. I know this from this information. Oh, another way of saying this is f of 1 equals 55. This is f prime of 1 equals 60, right? Those are really compact mathematical statements. And I find every semester, one of the things students really struggle with is the notation. Like if I could just ask you this in words, say, oh, no problem. This little compact mathematical statement, f prime of 1 equals 55, means when x equals 1, y is 55. That's just a point on the graph. When x is 1, y is 55. This little compact statement right here, f prime of 1 equals 60. That says when x is 1, the slope of the tangent line is 60. This picture here. It also says because it's positive, we know the function is increasing there. Very steep increasing. Okay, so I just gave you kind of a preview of pages 72 and 73. These are good ones to have when you're studying for the exam too. Make sure you understand the difference between F. Go through this page and look at the examples. They're really going to help you put things in context. And then F prime, page 72 and 73. I'm just going to preview a couple more pages here. Page 78 is a really good activity to go over. This is one that's for your homework you could do on page 78. Be good to call a study buddy in class and work through that. And I encourage you to talk about homework with classmates. Okay, next several pages we don't cover actually, so I want to point out ones you can put a big X through. Pages 80, big X through pages 80, 81, 82, and 83. We don't do the mean value theorem this semester. If you were a math major, that'd be important, but okay, then we're just about done the chapter. Again, at the end of chapters are these challenge problems. These are on dotted paper behind them. That's how you can find them. There's always a few at the end of every chapter, and it's a good idea as you're reading the chapter, actually start with these. Say, okay, let me think about a hiking trail. Let me think about, what's the next one? Oh, or vandalism, like detective story you have to go through. Read the level 1 problem here. If you want to do any upgrades, level 2, 3, 4, those are always optional bonus. Some of those I might ask you to do at least one, depends on the module. But you can get started reading those and thinking about those as you then go back to the beginning of the chapter and start working through your pages for activities for your assignments that are due and going through your videos. Okay, so that was chapter 1. And again, you get a lot more detail and more help with the activities as you go through the videos. And so keep those in mind, go back and forth between the journal and the video and the journal, and pause it, do a couple pages, continue on. I will post those as soon as we get out of class. I will update those dates on those so you can access them immediately after class. But in the meantime, any questions for me, logistics, module 0 things that are due tonight, content from today for module 1, and stick around if you're ready. You're free to go if you don't have questions. Otherwise, stick around and we'll work any problems that you want me to work.
So when you have like the original function, like 5x squared plus 50x, how exactly do you go about like getting to the derivative?
Great
Like
question.
if it's not given.
Great question. What's your name?
Connor.
Connor. Thank you, Connor. Okay, so Connor's question is, how are we going to go from here to here? And I keep saying that's coming soon, and it is. That's going to be coming in chapter 2. We're going to learn how to do this. For now, in chapter 1 in your assignments, you don't have to do this. There's a long way in chapter 1, something you'll hear about in the video called the limit definition of the derivative. Very long, but the original, it was Newton and Leibniz who discovered this was the way they thought about how to go from here to here, was something called the limit definition of the derivative. I want you to just watch those videos and understand it, but I'm not going to make you do that, because when we get to chapter 2, we'll learn that there's a very easy way to go from here to here. And we're going to do that. And so that's like another week from now, way down the road. Okay, a couple more questions in the chat. Diamond, so I will post this recorded video, again, as soon as we get out of class. It takes Zoom some time to process it. It takes YouTube some time to process it. So it'll probably be, maybe a couple hours before you can access this one. But as soon as we finish class today, I'm going to go in and change the start dates for the videos for module 1. So you should be able to, as soon as I'm done answering folks' questions tonight, so maybe 6 o'clock, 6:30, you should be able to access in module 1, there'll be like a video 1 on secant lines, a video 2 on tangent lines, a video 3 on limit definition of the derivative, a video 4 on average rate of change. You start working your way through those. And again, they should be accessible as soon as I get out of class tonight. Okay, next question. Kristen, hello. Yes, I'm glad you told me that. There's a couple other folks that just joined the class late. And so I need to put you in groups. If that doesn't happen, please send me an email, because I got so much going on and there's so many students to juggle in this class. So send me an email saying, hey, introduce yourself again. I'm Kristen. I need a group. And I'll do that also tonight. Nick, yeah, we don't do pages 80, 81, 82, 83. That's the mean value theorem. That's for math majors, not for business calculus. So you can put a big X through them or tear them out. Some students really enjoy the satisfaction of tearing those out. Macy, group challenge problems. So we don't have anything this week in module 1. Once we finish module 2, so that's actually like 2 weeks from now, your module 2, at the end of that, you have to do a group challenge problem. So I'll talk more about that next Wednesday. I'll have a lot more details in class on Wednesday. But the short summary is that your group will have a Google Doc. I have to go create those. Make a note to myself that I need to make these Google Docs for each group. And once I do those, you'll go into the assignment. It'll say in module 2, one of the last assignments will be your group challenge problem. You'll read the instructions, click on that link. It'll open a Google Doc that only you and your teammates can see, I can see, and the grader can see, and you'll start working through. You'll type in a particular font color, your teammate will type in a particular font color. You'll exchange ideas asynchronously, or you'll have a Zoom or a FaceTime with each other, and you'll start working through that challenge problem. But again, it's a good idea just to read them now and have them in mind as you're learning concepts and say, oh, I think our group should go for challenge 2, or I think our group, I like challenge 1. I think I totally understand it. I see how it uses tangent lines. And so that'll help you. It'll just help you prepare and save that work, which is coming at the end of module 2. Okay, Taylor, good question. Taylor's asking if you haven't heard from your assigned teammates. So let me know if that's the case. I think I'm going to have an option where you can, what's the word my husband used? Because there's something on a TV show. You can banish someone. So if you're not hearing from them, give them a shot, but also they might have to go solo and do an assignment on their own. I'd rather not do that because it's COVID. So Taylor, if you can, be as patient as you can this semester. Keep reaching out to them. Keep sending emails, or if you got their contact information some other way from the first class, send them a text or a phone. Just remember, it's a crazy time for everybody. So before you do that extreme step, let's try to give them a shot. Yes, yeah. So Taylor, probably if you got 3 of you, that's good. It could be that that 4th person has dropped a class. So there's a little bit of shifting here in the beginning. That's probably, so let me know if that's the case, but just give them a couple more chances. Cool.
One question.
Mhm.
For the team video, is there instructions how to make your own Zoom? I've never really done that before.
There should be on the syllabus, there's a little bit of advice on that, but basically that link on the syllabus goes to the College of Charleston has, what did they call this page? There's been so many new things during COVID, but the link on the syllabus will take you to a page that the College of Charleston has implemented to help students do these sorts of projects. And so you'll look there and see if there's any advice on making a Zoom. But the other thing is emailing your students and hopefully, or your teammates, and hope at least one of them has done this. The other option, I don't know who's asking this question. What's your name?
Aaron.
Aaron. Oh yeah, so the other option is you can use any other tool. Like if you know how to do it in FaceTime, if you know how to do a recording any other way, maybe even PowerPoints with just voiceover, can you talk that way? Doesn't have to be on Zoom, but I think Zoom is a good one to take your time or ease into learning and using this semester as a way to do that, because it's going to help you with the challenge problems. Probably it'll be a little bit easier than FaceTime. If you know how to do it, Microsoft Teams, any other way you want to do it, that's fine.
Thank you.
Mm-hmm. Okay, Max. Good. I think I understand your question. This is a good question. So Max is wondering about tangent lines. How do you know like which way to draw it coming off the function? And I think this is what you're saying, Max. Let's say I make this the point of tangency right there. So I can write it in the forward direction or the backward direction. It doesn't matter because the tangent line will be the same. So if I'm writing in the forward direction, I would sail off like that. If I'm writing in the backward direction, I would sail off like that. They should connect and be the same line. Trinity, thank you, Trinity. So let me see if that's, so Trinity's question is about the tech tool. It says that there is a Dropbox. No, I'm going to change that. I should change the instructions. That might be old thinking of mine. Let me make a note on that.
I saw that there was another assignment in one that was due on Sunday. I think it was like the flip book thing. When I clicked on it, it just said that there wasn't you didn't have to submit anything. But when I clicked on the tech tool, it's had a Dropbox for it.
Okay.
That's why I was
So-
asking.
I gotcha. Okay, so so I need to change the tech tool should be like the flip book. It should just say do it. I don't need to see it. I don't need to check it. So it should have similar instructions. I'll change that. Perfect. Thank you.